Hi. So Omer is a postdoctoral fellow at the University of Groningen, and his presentation title today is Origins of Life. Can Chemistry Be Alive? Omer has a PhD from the Weizmann Institute and is a postdoctoral fellow of the Dutch Origins Center. His research tries to bridge between chemistry and biology by learning principles related to the emergent behavior we call life. This is achieved by looking at different classes of synthetic chemical replicators, RNA, and bacteria. Omer, the floor is yours.
Thank you. So thank you for this introduction, and also thank you for organizing this and the opportunity to speak. And also thank you, whoever is listening now, either live or later to the recording. So what I would like to do is to have this talk more of a conceptual talk. So I will not go into a lot, or I will not go into any details, and it will just give you some taste of what is the origins of life and how you can address it scientifically, and maybe just a tiny flavor of my own research. Actually, if we just start with maybe one and a half take-home messages specifically about my own research, is that I am very much interested in how Darwinian evolution can happen in chemistry. We recognize quite a lot how it can happen and has happened in biology, in cells, but the question is, how can it happen in a system of interacting chemicals? And this might not be so obvious in this talk, but I will say it still that I'm not so much interested in figuring out the exact molecules, the exact structures that we need for life, but more I'm trying to find how can a chemical system give rise to emergent functions, and one of those functions is the Darwinian evolution. Now, let's go back. So when we think about the origin of life, or when we think about life in general, we are so hardwired to how we recognize the only example we have of life, which is us. And it can be quite difficult for us to think how it started. And this can be exemplified by looking at all those cool aliens from the different TV series and movies, that even though they are aliens and they have supposedly developed in very different roles, they all somehow share quite a lot of similarity with us, with the humans. So they all have a head and eyes, and they all have hands and fingers and so on and so forth. And even some of them are speaking English. But what if, at least at the origin of life, at least at the start of life on Earth, life started as something completely different? And the motivation to study the origin of life, well, first of all, it comes from the purely philosophic or romantic view of science. This is just trying to understand something better. But also, if we can understand the origin of life, maybe it would help us better understand what is life and how life developed. And maybe also it can shed a better or different light on how we can search for life outside of our own planet. And the problem is that life is quite complex. So to understand how life might have started can be easily as complex or even more. And this is exemplified by the following thought experiment, that if we start with this pool of amino acids, and as a side note, I will say that amino acids are important building block of life, and chains of such amino acids, they make up those proteins, and proteins are the workhorse of the cells. So if we think about how we go from this random pool of amino acids, and I'm not saying that this is how life began, actually life began probably very different, but just to convey the message, if we start with this pool of amino acids, and then we think what jump we need to make, for example, for the simplest bacteria, or what jump then we need to make, what complexity jump we need to make from that simplest bacteria that we can think of for a complex life, which is us, then actually it is largely believed that the jump from no life to life, from this pool of amino acids into bacteria, is far greater, far more complicated than the jump from this bacteria into us, even though we still don't really know how this jump from no life to life happened. Actually, even if we don't know how it happened, we can have some ideas on how it should happen, at least in principle. And well, one of them is that this is actually not so much of a jump. Because you can think you can think of the following example, that if you start here on the bottom, if you start with the workshop that has all the ingredients, all the right parts, from wings to bolts and whatever, that we need to make an airplane, a modern airplane, then we recognize that it is extremely unlikely, to say the very least, that some miraculous hurricane passed through this workshop, and then all of a sudden we had the emergence, the formation of an airplane. Likewise, the origin of life is not just a single step. Actually, even for this, for aviation, we recognize that maybe the father of modern aviation is the Wright brother airplane. Even though it's very different than modern airplane, and actually it couldn't even fly that much, still this is the father, the simple father of modern aviation. Now for me, in my own research, I'm trying to go even simpler than that. I'm really trying to go for something that can be seen maybe like the paper airplane equivalent of this. Really just anything can be as weird as it is or very different than what we recognize, just as long as it has the right features. But then what are those right features of life? Can we think of a definition for life? What are the most common ingredients for life? And we know that life is not just something static like this rock. Actually, life is something very dynamic. But also this geyser or this fire, even though they can be quite dynamic, and even more so, fire can spread quite easily, they are not considered alive by us. There is something more that's missing here. And what is something more is the ability to have some sort of an information and to pass this information to a progeny. So this information sometimes being passed, the copying of information, sometimes it is being passed with errors. And actually then some of those errors, luckily for us, can be quite positive and then lead towards evolution. So in fact, Darwinian evolution operates on those random variation that happen when you replicate yourself. So with that, we can think maybe, however difficult it is to define life as it is, just focusing about minimal life, something that is more relevant for the origin of life. So maybe two ingredients that are important for minimal life is the ability for a system, any chemical system, to self-replicate, so to maintain yourself in the environment and to be able to make more copies of yourself, but then also to be able to undergo Darwinian evolution. So when you make more copies of yourself, and those copies doesn't have to be exact copies, and then evolution can operate on those differences. So with that, we can think that the origin of life is this gradual transition. If we start here on the bottom left, it starts from the no life, and then the end of the origin of life, it finishes here on the top right. It is symbolized by Luca, the last universal common ancestor. Now, technically, the numbers here on the x-axis are very crude. Please don't take them at face value. But the Luca, the last universal common ancestor that symbolizes life as we know it, and as such, the end of the origin of life, is this very simple, extremely simple organism, extremely simple bacteria that is at the root of the tree of life. Now, the origin of life started with early Earth that had the right condition for life. It had the water, and it had a large variety of molecules. It had lipids, and it had amino acids, and it had sugars, but it did not have a life. And that stage of the early Earth is often called this prebiotic soup because it really was, you can call it a mixture of everything. And somewhere along this gradual transition from no life to life, what I'm more interested in is finding the first minimally living system. So really for me, any chemical system that is able to replicate and evolve can be a big breakthrough towards figuring out how life started. As a side note, I will say that when we take this when we look at this graph, then we can think that actually the origin of life, it had more of a chemistry phase, and then it had more of a biology phase. And I share maybe a different view. It is true that chemistry and biology have developed separately with their own tools and techniques and terminologies. But I think that because we are all part of the same reality, chemistry and biology can be just two sides of the same end, and there must be a larger rule set that sometimes we recognize it as chemistry and sometimes we recognize it as biology. Now, if you go back for this idea of replication and evolution, a question can be which came first? Because you need them both together, but which came first? So you can think that we have this sort of a chicken and egg question. And I'm deliberately not saying which is the chicken and which is the egg here, because I don't really know. But it is clear for me that out of self-replication and Darwinian evolution, one is the chicken and one is the egg. And the problem is which came first. So I think that actually it's not a problem of which came first, because they actually both came together. So the first system had to show both of them together. They are coupled somehow. So you can think that actually it's not that either the chicken or the egg came first, but in the origin of life, we are looking for this sort of a chain, a chemical system that is able to self-replicate and evolve. So now maybe in the last minute or minute and a half, I will just say a few words about how I'm technically more doing my own research, that I'm taking the network's perspective. So here you can think of a very simple example of a network. It can be, for example, the internet, the World Wide Web, where each of those circles, each of those nodes can represent a web page, and the arrows are links between them. So a link can be more central in a certain web page, and then it has a bigger arrow. Or there can be more links between one page to another that can also mean a bigger arrow. But in chemistry, you can also think of this as a chemical network. And then if this is a chemical network, then each of those circles, they are different chemicals. And the arrows between them, they represent transition. So maybe some molecule can get converted into another molecule. And then the thickness of the arrow is related for how efficient this process is or how fast this process is. Or you can even go something a bit more simple, saying that the arrows, they represent just some code interaction between them. For example, how they stick to one another. So maybe this network actually shows us how those molecules can assemble somehow to just form some groups together. And if you look at the network, then you can think that the network can be more connected, or a network can be more self-centered. Actually, if you think of a more self-centered network, even if you go to a more extreme, completely self-centered network, where all the molecules only interact with themselves, then it is likely that such a chemical system that is represented by that network might be quite good at self-replicating, at sustaining itself. However, when changes will begin to occur, when the environment will begin to change, maybe that system might not be so suited to deal with them, so it might not be so evolvable. Actually, I'm doing this both from the theoretical approach, but also both working with real chemical systems. And this is just one drawing of a chemical system where you have some different ingredients, and after they form those cycles, actually the network structure begin to emerge when there is a lot of interaction between them. And here, the network represents how they can share, how the different molecules can share components. I'd be very happy to give more references in the discussion later in all the social media, but there is actually, and with this I'm finishing, there is actually a real chemical system that behaves like that has been found and is being studied in the laboratory. And the key in this system is that the self-replication and maybe even the evolution, it is triggered by the self-assembly. It is triggered by not just how the molecule can move in space, but how they are stick to one another, maybe in ways that are dictated by the network structure. So with this, I hope that I was able to show you that the origin of life, first of all, it's an interesting field to study, and that you can actually go and study it scientifically, rigorously, and that there is actually a good reason for us to believe that maybe, either soon or later, but maybe we can sometime figure out some of the rules related for the origins of life. So with this, I want to thank again the organizers, and thank you who listened, and I'd be very happy to continue this discussion over all the social media platforms provided by this conference.